All right, now we're going to look at section 3, sampling distributions and estimators. I know, exciting stuff. All right, so we're going to look at sampling distributions of statistics. Well, that sounds weird. What that means is that we are going to look at the statistics of samples rather than of populations. So far, a lot of the things we've dealt with were populations, the mean height of men, the mean height of women, but how do we know that? How do we estimate that? We can't get the height of every single man and every single woman, and even if we were able to do that, it would automatically be out of date because people die, people are born, and so on. So, let's look at some general behaviors of sampling distributions. All right. When samples of the same size are taken from the same population, the following two properties apply. One, the sampling proportions tend to be normally distributed. That means if I look at, say, I'm looking at the height of men, and I want to know how many men are over 6 feet tall, say 1/4 of them are. Then I would expect if I take different samples, 1,000 men each or 100 men each, that I would get about 0.25 for some of those proportions that are over 6 feet. Some I might get 0.3, others I might get 0.2. But I expect that those proportions will be distributed normally about the proportion of the entire population. The picture will make this have more sense. Also, the mean of sample proportions is the same as that of the population mean. And we'll see what that means in a moment. All right, so let's take a look at proportions. Let's take a look at another proportion, something that has less to do with height and more to do with blue cars, because I like blue cars. Blue cars are good. What proportion of cars are blue? Well, let's say 20% of cars are blue. And I say that because I know all cars that have ever existed, and 20% of all of them have been blue. So 0.2 is a proportion that are blue. Now you pick 100 cars, you might have 18 that are blue, or 18 out of 100 that are blue. There might be another sample of 100 that has 30 out of 100 that are blue. But if I take all these proportions from all the different possible sample sizes of 100, then, and I plot, if I were to plot them, then I would get them normally distributed where the proportion of my population would be at the mean of this distribution here. And my proportions would be distributed accordingly. In other words, I'll have some samples that have a higher proportion than normal, and then I would have some that have a lower proportion than normal. Now, you'll notice that there is the population proportion, which is P, and then there's this P with a squiggly thing on it. That is read as P hat. So P hat of sample 1, P hat of sample 2, P hat of sample 3. All right. So the proportions are normally distributed. We have a mean, we have a standard deviation, they're symmetric. All the properties we've already talked about, normal distributions, we will see in this distribution. Next, the distribution of the sample means. All right, the sample means will themselves have a mean. In other words, the mean of the means will be equivalent to the sample mean. X bar, remember, is the mean of a sample. Mu is the mean of the standard deviation. And if we take all the possible different samples that we could have and took the mean of all these different samples, then that mean would be the population mean as well. This is going to be used later on. As a matter of fact, this is how most statistics are used, because population mean mu is very rarely known. So we have to use a sample mean. And the more sample means we have, the more definitively we can say what the population mean, mu, would be. But the means if they themselves are treated as data points, will also be normally distributed about the population mean. An example of this would be if we were to take the average heights of men, we'll go back to that, and we look at different classes, class 1, class 2, class 3, and we looked at all the classes. What exactly would they distribute about? So we'd have classes up here, basketball class, and we'd have classes out here, not basketball class, class where it helps to be shorter, maybe, I don't know, wrestling? Good division, something like that. Anyways, each of the classes would have a mean, and if you took the mean of the means, in other words, you averaged all, assuming the classes are all the same size, you averaged all the different class means, then you would get this mean here. Alright, so that is with proportions, that's what's mean. We do not have the same thing with variances. Variance distributions are skewed. So you'll notice that here we have the S's, and they tend to be right skewed. In other words, it tends to go further off to the right. And part of this is the fact that this will never go to 0. And so we'll have that. So this is what will happen with our little S squares. Remember, S squared is our sample variance, and our population variance will be sigma squared. Now, often when we look at these distributions, we shall look at them as either a histogram, or we can look at them as a probability density function. P at x bar or S squared. So this is just talking about the notation. P for population, P hat for sample proportion, population proportion. And so these are statistics, and remember, parameters are associated with the overall population, not with a sample. All right, behavior of sample populations. The distribution of sample proportions tends to approximate the normal distribution. We already talked about this, we already saw this. Sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions is equal to the population proportion P. Therefore, the more sample proportions we get, the closer we can approximate what the population proportion would be. All right, so an example. Consider repeating this process. We roll a die 5 times and find the proportion of odd numbers, 1, 3, or 5. So the proportion could be 0 out of 5 times, 1 out of 5 times, 2 out of 5 times, 3 out of 4 times, or 5 out of 5 times, or 0 to 1 in increments of 0.2. Okay, what is the behavior of all the sample proportions that are generated by this process? Continues indefinitely. And so we can do a small trial of 10,000 trials, so we would have 50,000 rolls at this point. And roll a die 5 times, sample population 1, 0.2, 0.4, 0.8, and so on and so forth. And we can see that we have, well, this one's kind of difficult to see, so alright, so here mu would be 3.5. We know this just from the fact that we know that each face has a 0.2 chance of showing up. Skipped a few there. Anyways, so this proportion, 0.2, 0.4, 0.8, we can see how they go. Most of them are not 1 or 0. We got 0.4 here, 0.5 here. They also are the highest, and they are centered around 0.5. And we have more that are 0.4 than 0.6. But we had a finite number of trials. We will expect it to always be a little bit off. All right. Now we can look at our means. So what is going to be our average for each of these 5? Again, we expect the means to have a normal distribution and the means to have a mean of the mean of the entire population. And that's what we see here. Average of each of these 5 rolls is, well, it could get at lowest 1 if we rolled 5 ones in a row, certainly possible. We could also roll 5 fives in a row, which is possible. But usually we're going to have means that are somewhere between 1 and 5. And they can be any number with an increment of possibly 0.2 between 1 and 5. 0.4, 0.8. And you can again see that this is a very nice normal distribution. This is what we would expect for the sample means. And as we can see, the mean of the sample means is close to the mean of the population, 3.5, and distributed normally about that. All right, sampling distributions of sample variances. All right, the sampling distribution of the variance with all samples having the same size n, taken from this population. We can use these equations. Population standard deviation will be sigma is equal to the square root of x minus mu squared over n, and population variance is simply equal to that squared. All right, these are equations that we have already used before. The behavior of the sample variance, the distribution of sample variances tend to be have a distribution that's skewed to the right. The sample variance target, the value of the population variance, that is the mean of the sample variances, is the population variance. So even though it's skewed, we still would expect that the mean of the sample variances would be the population variance. All right, we'll do the exact same thing here. And then sigma squared is 2.9, which is about where this mean is. We still see that it is skewed to the right. We have stuff drifting off to the right here. And we have nothing that's going to be to the left of 0. Hence, it is going to be skewed to the right. An estimator is a statistic used to infer the value of a population parameter. We just looked at 3 estimators. We have a proportion, we have a proportion of a sample, we have a mean of a sample, and we have a variance of a sample. All of these can be used to determine or estimate for the population. And these are called unbiased estimators. That is, it is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. Great. All right. So in English, what that means is that an unbiased estimator, we can get a lot of them together, calculate their mean, and the mean of that unbiased estimate, the average of all those unbiased estimators, is going to target or be close to, or we expect that it will be close to, that same parameter of the population. So if we're looking for the proportion of men who are over 6 feet tall, we can do that with samples. If we're looking for the average height of all Dachshund dogs, probably pretty short, then we could use that as well, do the average height of a bunch of samples. So unbiased estimator, proportion, mean, and variance. And we just showed that those were. So biased estimators, they do not target the value of this corresponding population. So we have median, which is just the middle number, range, and remember range is not particularly useful for the most part, and standard deviation, which is the square root of variance. So we do not we want to try to use those because those are going to be biased. Now, the sampling that we do sampling with replacement. So why do we do sampling with replacement? Well, the reason we do that, or at least we consider it sampling with replacement, is because our sample will usually be so small compared to the overall population that we can consider each of these results independent, even if we do not do replacement. It's just going to make such a small difference that there's no reason to consider it. If we look at the population of the United States, which is about 350 million people, and we do a sample of 2,000 people, even if we do not repeat people, the chance of someone being repeated anyway is small enough that we can consider each of those independent. So that would be a way to get a sample, 2,000 compared to 300 million. Now, if we tried to get the information from the census, that's not going to be a sample that we could do that with, because a census is trying to get all the information from everyone. That's also why a census is called a census. All right, and that is section 6.3. We shall continue on later with 6.4, the central limit theorem. Have fun.